Okay, just a quick check. Can everyone hear me?
Yes.
Okay.
Yep.
So for any co-hosts going to record, you can go ahead and restart recording. Just to double check, this is the last slide we left off with, yes or no? Nobody remembers?
Yes, it is.
Okay. So we don't need to focus so much on this. You already know the relationship between zinc and copper here. The main focus is just about the relationship between E cell at standard state, delta G, and your values of K. Okay. Same thing here. We spoke about this relationship between K, E cell at standard state, and then the relationship all with delta G as well. Okay. The only thing that I do want to talk about after this is something called concentration cells. For those of you taking the lab, you will be making concentration cells. I'm assuming the labs are the same. If they have changed it, then you may not be doing this one. But the main point of a concentration cell is that it is the same metal. So instead of using two different metals, such as like copper and zinc, I have two of the same metals. So two coppers, essentially. The only difference between the two coppers is that one has a higher concentration and one has a lower concentration. We're actually exploiting that information. We're exploiting the differences in concentration. It's going to try to reach equilibrium where both concentrations become the same. And how it's going to do that is, remember when we mentioned here, so the solid will break apart into the ion form. In other words, this concentration will increase, and then we will also form electrons in the process. And on the other end, this ion is going to join with the electrons, forming our solid. So once again, the one with the higher concentration is the one that's going to end up using up the electrons, forming the solid. And the one that has a lower concentration is going to break apart its solid, its electrode, and form more of its concentration. Any questions? Okay. With that said, the good thing about this is that our cell potential, oh, sorry, not in that spot right there. Once again, our cell potential, E cell at standard state, is going to be equal to 0. And the reason why it is equal to 0 is because the cathode minus the anode is going to come out to 0, because both numbers should be the same value. Any questions? Okay. So with that said, my overall E cell is going to be positive. That's what we want for a spontaneous reaction. But my E cell at standard state, so this value right here, is going to be equal to 0. So our half reactions are just the same exact thing. It's just kind of flipped. So you flip the equation. Only difference is the concentration that is there. Okay. Anyone have any questions so far? Okay. So I want you to give this problem a try. You have here two silver electrodes. So essentially, this is a concentration cell. So two of these half reactions, they're both silver. So one of these is a 0.01 concentration. The other one is 4.0 times 10 to the negative 4 concentration. Just really quickly, is anyone confused about what we are doing? Okay. How many of you would like me to go through the problem with you for this one? Okay. So I'll do this one directly with you first. And then if there is another one afterwards, you can try that one on your own. Okay. So I have two concentrations. They both are essentially the same thing. So I have silver over here and silver over here. I'm going to refer to this as silver concentrated and silver diluted. Okay. So that's kind of indicating what I have here. Based on the two concentrations, this one is essentially 10 to the negative 2. And this one is 4.0 times 10 to the negative 2. I'm sorry, 10 to the negative 4. So this one is the concentrated one. This one is the diluted one. And what's happening with this first one right here, right? They actually label it as A and B. So we'll call this one A and we'll call this one B. What's happening in the concentrated one is that the silver is going to change from the silver positive ion, right? It's going to receive electrons. And when it receives an electron, it's going to go ahead and form the silver solid. And on the other side, this one is diluted. So this one's going to take the silver solids that it has, in other words, the electrode, and it's going to break apart into silver ions. And this is going to keep happening on both sides. This is going to give away the electron. This is going to receive the electron. This is going to happen until both sides have the same concentration. Any questions? Okay.
Wait, Professor.
Yes.
Could you Tell me why one of them receives electrons and one of them gives off electrons.
Okay. This concentration right here, 10 to the negative 2, is bigger than this concentration. Can we agree on that?
Yeah.
Okay, if there's a big difference in concentration, what's happening is the one with the higher concentration is going to give up the ion form. The ion form is where we look at the concentration. Does that make sense? This is an aqueous form.
Mm-hmm.
So this is going to get used up. It's going to join with the electron, and it's going to make our silver bar.
Oh, okay.
Okay, and the other side, because the concentration is lower, right? So this is a lower value. You're going to use up the metal bar that you have here, and it's going to go ahead and form more of the ion.
Okay.
Okay.
Yeah. Got it.
All right. So once again, in half cell A, we're going to go ahead and try to decrease the concentration while we increase the concentration in B. So we set it up the same way. This is our overall equation. So this equation should look very familiar to you. The number of electrons being transferred is 1, so we'll just keep that at the bottom here. We're under the assumption that this is at 25 degrees Celsius, so this is our log of our Q value, right? So I don't need to deal with the ln, and I don't need to deal with the R value, the F value, things like that. I simply remove all that, make it into my 0.0592 over n. The other good thing about this is that this value right here is equal to 0 because E cell of itself minus itself is 0. So I can remove that entire piece. So this is down 0. Okay. So all I need to do to solve for my overall E cell is just simply this equation right here and log of Q. Any questions?
Can you repeat why is E standard cell 0 again?
Okay. So whenever I'm solving for an E cell, this is the standard reduction potential, right?
Yeah.
So I'm looking at, I'll just give you an example. This is for my cathode. I'm going to make up a number here. This is maybe like 1.86. Okay. And then the other thing happens to be my anode. So I'll say it's 0.95. Oh, sorry. 95. Okay. And this is for my anode. Normally I would do this minus this, right? Let's say this happens to be for zinc. This happens to be for copper. I'm just making up what it is. Okay.
Yeah.
And the one that's more positive subtraction from the one that's more negative.
Yeah.
Do I have two different elements?
Oh, okay. So because here it's the same element, that's why it's 0. Okay, got it.
So it's
Thank you.
essentially, if I wrote this number was 2.5, it'd be 2.5 minus 2.5, which
Okay.
gives me 0.
Okay, thank you, Professor. Yeah.
All right. Anyone need more time to copy this down? Okay. Big hint for your lab. The bigger difference in concentration, the greater the voltage you're going to get because more of that electron is going to transfer. The smaller the difference between your concentrations, the smaller your voltage. That's just a hint for your lab. Assuming it's the same lab. Okay. It looks like we don't have any other questions for the concentration cell. So we're just going to talk about the next part, which is known as your batteries. Okay. For your batteries here, we have two main types. We have a primary battery and we have a secondary battery. Primary battery cannot be recharged. It only has one function, which is 2 half cells to transfer from one direction and cannot be reversed. Once it reaches equilibrium, no more electrons are transferred. So in other words, electricity is out. It is now considered a dead battery. So you have some of your generic batteries like your Duracell batteries that are not rechargeable. Those are your primary batteries. A secondary battery is where it is rechargeable. So it has the forward reaction and the reverse reaction. And what happens here is if you have to supply it with enough energy to go ahead and make it undergo the reverse reaction, then you can go ahead and use it again. So if you've ever been inside of a Radio Shack from X many years ago, they always sell rechargeable batteries. But any battery you use that's rechargeable, over time, it wears down. Same thing with the laptop battery, same thing with the car battery, any of the above. So over time, it will wear down because you need to put in more energy than you receive out of it. And then there's corrosion along the way as well. Okay, so we're going to go through a couple of examples. You don't need to know these in detail, just kind of have a general idea of them. So you have the alkaline battery. This is a standard primary battery. This is the ones you see in Duracell. It goes forward in one reaction and that's it. It doesn't allow any reversal here. Okay. The other one is your silver button batteries, is ones you found inside of your watches sometimes. Once again, these are also one-time use. Same with you if you have a car and you have that car alarm or the button pressing, it's the same thing inside. So it's a one-time use. It cannot be recharged. Okay, lithium battery pacemakers inside of people when they have pacemakers also needs to be replaced. So lead acid batteries, sometimes certain lead acid batteries in cars these are rechargeable. In other words, these are secondary batteries. So they have two functions, and they have the discharge and then the recharge portion. So these are rechargeable. In other words, they are secondary batteries. Nickel metal hydride batteries found inside of power tools. These are also rechargeable. So there is usually a base system that you go ahead and plug this in to recharge this thing. Lithium ion batteries found inside of your laptops are also rechargeable. Just as with all batteries, anything that's rechargeable is subject to corrosion and wear and tear over time. So it's not going to be as effective later on. All right. The next thing we're going to talk about is the electrolytic cell. So electrolytic cell, remember, this is the one that is non-spontaneous. It is the one that you have to go and put in energy to make the reaction go in that direction. Okay. So let's say this is a non-spontaneous reaction. The reaction will never go from A to B unless you put in energy. So once you add in energy, it finally makes it go forward from A to B. So you're using electrical energy to drive a chemical reaction forward. So everything is the same exact thing. Oxidation still happens with the anode. Reduction still happens with the cathode. The only difference now is that my electrodes, my cathode and anode, are now flipped in signs. So it's no longer positive at the cathode, it is now negative at the cathode. An example here, this is my standard reaction that I have here. This is my galvanic cell, voltaic cell. If I left this to be on its own, it will generate a voltage of 0.48 voltages. Okay, so this is how much energy I can get out of it. If I attach this to some kind of outlet, for example, and I put in energy that is greater than 0.48, it can force the reaction to go backwards. So if you look here, this is the reaction going backwards. I'm actually undoing everything that I did here. So in other words, we're going in the reverse reaction in this scenario. Okay, any questions? Now, with that said, if I go in the reverse reaction, what is happening here is that I am forming more of the tin from the solution. So this is essentially going into the tin bar. And the other scenario was when I made more copper. Okay, so we can actually force these kind of reactions to happen, and we can actually use it in examples of like gold plating. Okay, so you can force gold to essentially rejoin with the solid form. So it kind of covers whatever the item was, and it forces the gold to form into the solid form and back into the metal essentially. So this is how you go ahead and do gold plating. Once again, talking about the lead acid battery, we have the discharge portion and then the recharge portion. So this is your two cells essentially. One is your voltaic cell, the other one is your electrolytic cell. So one is the one that essentially happens spontaneously, uses up the energy, you're just extracting it. And then if you want to recharge it, you force enough energy into it to overcome the amount that it is generating. So you kind of force the reaction to go backwards. Okay, any questions? All right. With that said, we can compare the two of these. The only main difference between electrolytic cells and voltaic cells is the signs here for delta G, because that's referring to spontaneous versus non-spontaneous. E cell, the same exact situation. And then these signs right here. So what was positive is now negative, what was negative is now positive. And if it was a spontaneous reaction, this is a non-spontaneous reaction. Okay, anyone have any questions so far? All right. Yeah, go ahead.
So for the voltaic, not the voltaic cell, for the electrolytic cell that you just showed in the previous slide, do we have to remember the equations of how that works and everything?
It is the same as your voltaic cell, just the opposite.
Okay.
So instead of generating 0.48 voltages, right? Well, you can pretty much figure out how many voltages are generated, how much the E cell value is, right?
Yeah.
So to make it an electrolytic cell, you are putting in that many voltages or more to make it essentially go backwards.
Okay.
Okay. In most cases, at least in terms of chemistry and people who are studying this, they want to extract energy that is spontaneous, that is free. If you have to put in energy, it's usually not worth it unless you're trying to do something very, very specific.
Okay. Got it. Thank you.
Okay. So some products of electrolysis, we can actually split certain salts. So like sodium chloride. Tell you something about sodium chloride is that it exists in nature as sodium chloride, but you do not find chlorine in nature by itself. You do not find sodium in nature by itself. So they don't exist as a free state. So you'll never find a piece of sodium sitting around somewhere. You never find chlorine gas floating around somewhere. These are all essentially man-made and forced to happen. And we can do this by essentially using electrolysis. So you're electrifying the salt, the molten salt. So it's a liquid form of salt. Then you can go ahead and extract the sodium out of it. And sodium itself, if it's just regular sodium, it is very, very reactive. So if you put it in water, it gets explosive. And you can also extract chlorine gas out of this. So this is one way of separating the two and not separating the ion form. So normally if you put it in water, you get Na plus and Cl minus. This is essentially getting you Na0 and then Cl0. So the not the ion form, but the actual atom form. Okay. With that said, we can also separate water. So normally water is made up of two things, hydrogen and oxygen. They are very, very distinct. Oxygen is something you breathe, water is something you drink. Hydrogen is something you put in rocket fuel. It's very explosive. Okay. But seeing that you have water, it's very hard to go ahead and separate water into oxygen and hydrogen. So normally on any basis, even if you tried heating it, it will only turn it into steam. It will not separate the actual individual atoms from each other. Okay. But with electrolysis, you can do that. So with electricity, you're essentially forcing all the positives go to one side, all the negatives go to the other. And hydrogens are more positive, oxygens are more negative. So they're going to go ahead and pull to the other side, and you will essentially separate oxygens to one side, hydrogens to the other. So if you look here carefully as well, you'll notice that this is twice the amount compared to the oxygen. So that's telling us that this should be essentially H2O, 2 hydrogens for every 1 oxygen. And you can actually buy these kits online. They're really cheap. You use some battery source to go essentially force electricity into this, separating the water, forming hydrogen gas and oxygen gas. If you were to light this little bit of hydrogen gas, it would make a pop sound. Okay, any questions? All right. Also, another example of electrolysis or using electrolytic cells is just, again, gold plating. So you'll see like plated jewelry. Let's say the inside is not made of gold. They cover the outside with gold. They use the same process. So they use electricity to force the gold onto a particular metal. So with that said, we're going to talk about some ending reminders. The half reaction method that you use, it's essentially your basic solution steps are just your acidic steps plus a few more steps. Okay. Make sure you know how to draw a voltaic cell, or also known as galvanic cell. Know about the line notation. Know about just reading the overall equation. Okay. Your cathode is a positive one, anode is a negative, and this is for your voltaic cell. For electrolytic, it is all flipped around. Your free energy equilibrium and your cell potential are all related. You can convert between one or the other, and you can ask Nernst for help with that. And the Nernst equation, the best way to use that equation is, once again, if you have 25 degrees Celsius, you know that it becomes 0.0592 over N. And remember that rechargeable batteries consist of voltaic and electrolytic cells, one for discharging, in other words, you giving away electricity, and the other one for recharging, allowing you to add electricity back in. Okay, anyone have any questions so far? All right, anyone need time to copy this? Okay, so some mnemonics to help you remember things in chapter 21, because there's a lot of stuff happening, and then there's positive and negatives. One way to remember this is Leo says GERD. In other words, loss of electrons is oxidation, gain of electrons is reduction. And then also remember NOx, red cat. That's telling you that the anode has oxidation, and then the cathode has reduction. Okay. We will actually start this topic right now. We'll do a little bit of review for our final exam today, tomorrow, and every time until the final exam itself. Okay. With that said, there are also, this is a little out of date. These are from my previous semesters, but I believe the evaluations are actually already open. So the QC evaluations, they send emails, they send multiple emails. What I'm going to go ahead and request for all of you is that if 90% of all of you complete that, you can write whatever you want in it, not extra credit. So what I'm going to do is if 90% of you complete it, right, those 5 points you get for attendance and polls and everything, some of you probably missed some polls, didn't do so well on them, missed some classes, you will automatically get those 5 points. If 90% of you complete the evaluation, all of you will get those 5 points in full. Okay, so that is my rule for that. Okay, with that said, there's also Rate My Professor. You can write down things that, I don't smile, Alex is crazy, beware, anything you want to go ahead and add. All right, with that said, don't stress about electrochemistry. The link is just found. I think you just type in qc.cuny.edu/evaluation or something. Okay. They are graded on partially completion, so I'm not going to be super mean about it. Like if you get like 3 out of 4 of them, 4 out of 5 of them, most of the time, I'll give you the full credit. Okay, but if you're getting like 1 out of the 5, then I'm going to start taking off some points. Or if you don't fill them in at all. And once again, don't stress about electrochemistry. You will have great potential. No, I am not going to waive another quiz grade. Jonathan, there is a purpose to the Alex extra credit. We'll talk about that when the time comes later on. Okay. Okay. With that said, I'm going to give you a couple of options. The options are for our review right now, we can essentially go over concept first. So we spent a lot of time just doing concepts from chapters 12 to 21. Or if you want to do a couple practice questions that I have created, we can do those. Or if you want, I have a sample final exam. We're going to do all 3 of these things, but it just depends on what order you want to do them in. Okay, so choices are, once again, I'll type in the chat so you can see. Okay, we can go over concepts. We can go over questions that I made or sample final exam.
Also, Professor, is it in person or online? Because CUNY first says it's online.
Are you referring to the actual final exam?
Yes.
As far as I was told, last I've heard was in person. So I'll confirm with them later on. But as far as I was aware so far, I was told that we were meeting in person because I know exams are supposed to be done in person. And just luckily for us that we only had 1 exam. Everything else is quizzes.
Professor,
Yep.
I have a question about the Alex grading system. So do you want me to stay in the office hours for that?
Yeah, you can ask then.
Okay, thank you.
Okay. Okay. So just to clarify, I do recommend going over concepts first to make sure you understand the stuff. Remember, we're going to go through all 3 of these no matter what. Okay. So my recommendation is concepts. I do see a lot of people are saying samples. I don't see anyone really saying the questions that I made. So we can hold that on to later. So once again, just even if you type before this, if you want concepts, just go ahead and type right after I say concepts. Okay. So about 4, 5, 6, 8 people so far, right? And then those that want to go over practice final exam. Okay, looks like majority so far want concepts. So before we start the concepts, I'm actually going to give you your poll. Okay, so go ahead and just fill out this poll, and then we're going to get started with the concepts. Okay, I'm going to end the poll in about 1 more minute. Okay, I'm going to go ahead and close the poll now. So if you haven't finished it, hurry up what you're finishing, about what you're finishing. Finish what you have to finish. Okay, so let's talk about the poll real quick. Seems like most of you want either more practice questions or move at a slower pace. That is good to know. Thank you for letting me know. For the next one, what can we conclude about concentration cells? And the answer is actually E cell at standard state. So it's the second one. Only about 50 of you got that correct. And for the last one here, what do you think about your overall grade? I see most of you saying that you might be getting a B. Some of you saying C. Thankfully, no one said D. Okay. All right. So let's get started. This is a review of every single thing we've covered so far, chapters 12 all the way to 21. Most of this is just going to be slides that you already have and you are familiar with. So my thing about making a separate recording with Zoom is that a lot of times when I stop the recording and then I restart the recording, it doesn't save the first recording or it loses the second one or the other. So it's risky in that sense. What I can do is if this all saves correctly, I will download it twice, separate them into half each, and then we'll go from there. So I'll give that a try. Okay. All right. So first, we're going to talk about chapter 12, intramolecular forces. Is focused on the liquid, solids, and the phase changes. If you remember the intramolecular forces, so these are the ones inside of the actual bond. So like hydrogen bonded to oxygen for water. These are way stronger than your intermolecular forces, so between molecules. To give you an example again, not necessary for that part. Sorry, just to answer someone's question. Okay, so once again, I have the reaction, the relationship between two waters. This is known as your intermolecular force, but the bond itself for forming this hydrogen with oxygen right here, this is your intramolecular force. So this right here are these forces that I'm talking about here. They are much more stronger than the attractive forces between two molecules. Okay, and we can tell by the number here, if we look at the amount of energy that we have, this goes up to 1,000 easily, down to 400, down to the lowest is 75 here. Okay, with that said, when I look at my intermolecular forces, the highest this will go is up to 600. So generally speaking, these forces are significantly weaker compared to my, well, these forces are significantly weaker compared to my intramolecular forces. Okay, any questions? This is the time to ask. Okay. So the main intermolecular force I'm going to focus on is going to be hydrogen bond. So hydrogen bond is going to be the strongest one outside of ion dipole. Okay. So hydrogen bond is essentially a dipole-dipole. So all of these are dipole-dipoles except for your London dispersion forces. Your dipole-dipole just simply means that there's a difference in electronegativity. One has a higher electronegativity, one has a lower electronegativity, so that the difference is shown up in the molecule. So an example I can give you is I have just HCl here. Between these two, chlorine is more electronegative. So the electron is going to lean more towards the right side. So most of the electrons are going to be closer to here and less around the hydrogens. They're going to be closer to the chlorine. With that said, this side can be more negative, this side can be more positive. And when it comes to hydrogen bonds, the only difference is that it is a hydrogen bonded to one of these three. So we'll just use fluorine, for example. If I look at this, because this is even more electronegative, the electrons are all leading much more closer to fluorine. Very little is going to be close to hydrogen. So this is still negative, this is still positive. But remember, these are partials, okay? So the simple partial is given like that. And the reason why we write that partial is to show you that this is not a full negative, full positive. Full negative, full positives are NaCl plus and Cl minus. So it's completely taking the electron. This is completely giving away the electron. These are not the case. These are sharing their electrons still. It just so happens that they tend to lean more towards chlorine. This one tends to lean more towards the fluorine. If you count ion dipoles as well, then ion dipoles are the strongest. Then it's hydrogen bonds. So if you have an ion present, in other words, you have a full positive present, then it will have a stronger force, intermolecular force than hydrogen bonds. But generally speaking, if you're only looking at covalent forces, like when they're sharing, then yes, hydrogen bonds are the strongest of the covalent forces in intermolecular force mind process, okay? Also, with that said, once again, because this one is hydrogen bond, more of it leans towards the fluorine. That means this is more negative, this is more positive. So I like to almost draw this as a partial double positive, partial double negative to show you that this one is much more stronger than a regular dipole-dipole. And once again, most of the time we're referring to the strongest force, but there are also weaker forces present, but the one we focus on is the strongest. If I asked you for what all of the forces that are present, you would tell me, in this case, hydrogen bonding, dipole-dipole, and London dispersion forces. If I asked you for the strongest one, you would simply just tell me hydrogen bonding. Any questions?
Yes. So if we are asked to to arrange the highest forces of attraction in any molecule, and if there are hydrogen presence of hydrogen bonding, so we'll say first one is hydrogen bonding, and then the dipole-dipole or ion dipole, or the one that you're writing.
So ion dipole is going to be first no matter what, because that is an ion itself. You're almost looking at this almost kind of like an ion bond, okay?
Okay.
Which is almost borderline intramolecular force.
Okay.
And you
got
have
it.
hydrogen bonding, which is essentially, these two are the same thing. This is just a stronger form of this.
Okay, got
Okay.
it. Okay, thank
And
you.
then dipole-dipole exists as long as there's a polar molecule. London dispersion forces exist everywhere. They are
Everywhere.
the weakest force, but they are present no matter what.
Okay, thank you, Professor.
Okay. You can also tell from down here, the solid lines are your covalent bonds. So this is some kind of molecule. This is the attractive force between those two molecules. Okay, so these are two different molecules. This is the attractive force. Okay, with that said, this is your dipole-dipole. Again, one side is more electronegative compared to the other. So that's why they tend to lean to one side. So the negatives on this side, positive on the other side. And then there's that attraction to another positive. Remember, this is between two molecules. So if you only had one molecule and nothing else around it, this can never form any dipole-dipole. This can never form any intermolecular force. It requires at least two molecules. Okay, once again, the best way of breaking this up, are there ions present? If there are, then we're looking at ionic bonding or ion dipole forces, okay? So that's kind of like this branch here. We break that off, move it to the side. If we look at that there's no ions present, then we separate into polar versus non-polar. If it is polar, it is dipole-dipole. And then we have to look if there is hydrogen covalently bonded to nitrogen, oxygen, or fluorine. If it is, then we have a stronger form of dipole-dipole, which is known as hydrogen bond. If there are no forces, if it's non-polar, we look at dispersion forces only. Okay, so you don't need to worry so much about this one. Dipole-induced dipole, it's very, very minor. We don't need to worry about that. Focus more on polar molecules versus non-polar. This is your London dispersion forces. Once you get to a place where both sides or both molecules you're looking at have the same force, then you look at the size. So in other words, the mass. Then after that, you look at the shape. Okay. The reason why we care about this, once again, is because it affects our physical properties. So a lot of these slides you are already familiar with. We're just revisiting them. I'm re-emphasizing certain points. If you have something you don't understand, this is the time to ask, okay? So strong intermolecular force, everything else increases except for your vapor pressure. Vapor pressure is the only thing that decreases. So if this goes up, everything else goes up except for vapor pressure. All right, with that said, let's continue. There's two types of graphs in chapter 12, the heating cooling curve and then the phase diagram. Make sure you know the difference between the two. So for a cooling curve in this particular case, you're dealing with the heat. Sometimes they just call this reaction, and then they just simply write forward. So this is just a reaction going forward. And then they have the temperature changing on the left side here, or on the y-axis. And you're always going to have 5 parts, okay? In total, you're going to have 5 parts. These flat lines, there's no temperature change. This is where you have a phase change. And then, George, you have a question?
Yeah, I just have a really quick question. That means, let's say, it asks, I don't know if this might be on the exam. What if it asks something like plasma? What would that fall
It will
under?
not ask you
It
for
will not
plasma.
ask us.
It
Okay.
will not ask for plasma. You can learn about plasma in physics.
Okay, thank you.
Okay. So once again, anything that's a flat line here is a phase change. So it's a change between 2 phases. Anything that's a diagonal line, there's a temperature change. You know that you're dealing with your MCAT equation. Okay. And the C is different from every single one of these. Temperatures different depending on what you have. So when you do this, remember that you always want to make sure that any value you put in here, any Q value, the heat value, if you're putting these as positive, you keep it all as positive. Okay. So yeah, in this case, if you look at it, this is going in the decreasing method, right? So everything here should be negative. But when you calculate this should also be negative. So you want to make sure that if they are negative, you want to put it as all negative. So when you add the total together, you're not doing a negative and a positive and then a negative and a positive. You want to make sure they are all negative. So when you finally found out the value, you have a total mass that makes sense. Or a total sum that makes sense. Any questions? Okay. In most cases, they should provide that. But if it's for water, I recommend that you know it. So delta H vaporization, what is our value for that? If you can remember those
Is
off
it
the top of your head.
4.18?
It's 40.7 kilojoules per mole. And that's for this value right here, right? Or it is 2,260 joules per gram. And then the one over here, this one, I believe it was 6.7 kilojoules per mole, or 6.07. And then this one down here was 334 joules per gram. Now, to just make things a lot more easier if you remember the general idea. Okay. And you'll also realize that this one right here is significantly larger than this. So the energy it takes to go ahead and melt something is much more less than the energy it takes to boil something. It takes a lot more energy to boil something than it does to melt it. Okay. With that said, these are the 2 equations you're going to work with, your MC delta T, or your MCAT, and then this one is your phase change. So it is the amount, either M or N, times that delta H. If they give you a delta H value, or if they give you something that is not water, then they have to provide you with the delta H values. In other words, the delta H vaporization or the delta H diffusion. Otherwise, you cannot solve it. And moving on to phase diagrams. Phase diagram is pretty straightforward. It's a relation between pressure and temperature. There is a triple point that you can recognize that's unique to just phase diagrams. So all 3 phases exist at equilibrium here. And you also have a supercritical fluid. And then other thing you have to pay attention to is this line right here. If it is positive, then it tells us that the solid is more dense than the liquid. In other words, the solid will sink. If it is negative, so in other words, it goes like this, then it tells us that the solid will float. Okay, any questions? All right. So moving on to chapter 13. The main thing is just mostly calculations. So you need to know molarity and molality, why there's a difference between the two, which one is dependent on temperature, which one is not. And remember that molarity is dependent on temperature because volume is dependent on temperature. So that will change. Molality is independent of that. It's only mass and mass, or moles and mass, which is the same thing as mass and mass. So with that said, you also need to know parts by mass, mass percentage, parts by volume, parts per million, parts per billion, mole fractions, all of these here. So you need to know these equations inside and out. Anyone have any questions? It is the kilograms of solvent. Yes. Not always the liquid. Sometimes it may not be a liquid. So you can't always quote it as being the liquid. In most cases, it is the liquid, but not always. Okay. Okay, you also need to know osmotic pressure. Now we're going to start talking about colligative properties. Again, the colligative properties are just expansions on things you know from concentration term. They always have something from the concentration term. So this is your molarity from your concentration term. So you can't solve for this if you don't know molarity. So know your concentration terms first, then tackle these. And just to clarify about the R's here, okay? Anytime I'm dealing with pressure or gases, I am dealing with 0.0821 ATM is another hint. That's telling you that this is the pressure of a gas. Okay. If I am looking at 8.3145, this is joules per Kelvin. So in other words, this is dealing with energy. So one of these deals with energy, one of these deals with pressure and gases. So make sure you know which one is which. Go ahead, George.
So for where it has the ATM L mole per mole per Kelvin, how would that be said? That would just be atmospheric pressure per liter, or atmospheric pressure per liter per mole per Kelvin.
So let me explain why these units are here. Okay. So
Mhm.
to clarify it, if you look at this equation, this is my osmotic pressure, right? This value. Okay.
Yeah.
This is some kind of pressure. All right. I'm going to leave that there. Okay. On the other side, I have molarity. How do I write molarity normally? What are the units?
Molarity is like grams per mole. Oh no, moles.
Moles per
Is it moles per gram? Do I have it
Moles per
backwards?
liter.
Oh, moles per
Liters.
liter.
Okay. Now, what about temperature? What unit is that usually?
Kelvin.
Kelvin. Okay. So if you look carefully here, these are all on the same side, right?
Yeah, and then they would cancel out.
You would cancel out the pressure and the other pressure because you would go ahead there both on both sides. Make sense?
Yeah.
Okay. Now, liters per mole is the inverse of moles per liter. And since this is on the same side, they
Okay.
would essentially cancel out because they're on the same side.
Okay.
Now, this is
So then it would just
over
be in
temperature
Kelvin.
with over Kelvin, and this is Kelvin. So then that means Kelvin over
Oh.
Kelvin would be canceled out. So that is why we write the units the way they are here. The constant here is to cancel out those different values depending on which one you're looking at and which one you're solving.
That makes sense.
Okay.
Yeah, thank you.
Temperature is always Kelvin. They will never ask you for Celsius. Even if you convert everything to Kelvin, you will still be able to find what you need in Celsius. Most of the time, they'll ask you for change in temperature, which even if you convert to Kelvin, it is still the same value. So an example I can give you, if I said I wanted you to go ahead and find 0 degrees Celsius to 100 degrees Celsius, if you were to convert all of this to Kelvin, this would be 273 Kelvin to 373 Kelvin. So the difference between the two of these is still 100. Does that make sense? Okay, when you take the actual ACS, they will provide you with an ACS data sheet. So in other words, there will be a reference table. It will have some equations on it. I don't believe it has any of the concentration terms on it. So that is something that you have to memorize. It will have equations, probably like your Nernst equation might be on there, if I can vaguely remember it. Okay. Moving on, boiling point elevation. This is one of our another colligative properties. Remember that this is molality here, okay? And once you solve for delta TB, we're not done yet. This is how much it is changing by. And since I am dealing with the boiling point, I am adding this to whatever my boiling point is. So if my boiling point happens to be 100 for water, then I add whatever this changes to 100. If the boiling point is something else for different substance, I change that value, okay? Any questions?
Professor, can you just stay on the side for 1 more minute for me to copy it down just to double check?
Sure.
Thank
And the
you.
other one we're going to talk about is freezing point depression, which is the same thing, just equation-wise, it is delta TF equals KF and then M. And the only difference is that this is freezing point depression, so it's going downwards, okay? What that means is if I'm dealing with water, it starts at 0 degrees Celsius and I'm going below 0 degrees. If I'm doing another substance, I'll pick whatever that value is and then I go below that value. So in most cases, if you are dealing with water, right, and you have some kind of salt added in, you have a solution. Your freezing point should be less than 0. Your boiling point should be greater than 100. If you don't have that number in place, if you have something else, like let's say you wrote 75, then you are wrong no matter what. Okay. Okay. You do not need to solve for KB by yourselves. It is a constant. So KB is 0.512. KF is 1.86 for water. Anything else that is not water should be provided for you. Does that answer your question? $1.86. Okay. So once again, freezing point depression, same exact thing. I just explained it, so we don't have to stay on this slide. Really quickly, there's also vapor pressure lowering. This one's pretty straightforward. It's just the change in the P here is equal to your mole fraction of your solute times your pure solvent. Or if I am looking for the P of solution, so the pressure of the solution, this is equal to the mole fraction of my solvent times the pure solvent. Okay, and also our I factor. Remember, our I factor here is very important. This is going to tell me the number of particles that are present. In other words, it will affect my values here, whatever these values are, by that many times. So if my I was equal to 2, then this is essentially twice the amount, each one of these. So that is a big difference. So the more particles you have, the more effective it is. Okay, any questions? All right. Now moving on to chapter 16. Once again, chapter 13, the main focus was going to be on those calculations. Okay. Again, this doesn't cover every single thing, but this covers most of the main points. So if you understand everything we've been talking about, you're in good standing for the upcoming final exam. Okay. So you want to determine the reaction orders. This can only be done through the experimentally. So you cannot calculate this manually unless you're dealing with an elementary step. But generally speaking, this is done experimentally. So you're trying to figure out the orders, which are the M and N, in other words, the powers. Okay. And looking at the equation itself, this is not like equilibrium. Looking at the equation itself does not give me the information for that. Okay, so an example here. If you can visually see this just by looking at it, then that's great. If you cannot, you want to plug it into an equation and solve it that way. Okay. So let's go ahead and take a look at this. A good example to look at would be experiments 1 and 2. I'm looking at experiments 1 and 2. I always recommend putting the later experiment on top and then the earlier experiment on the bottom, just because concentration wise, these are usually higher than the previous ones, or they have a faster rate than the other one. So that gives you more of a whole number. So if you wanted to do this old fashioned way, you see that B is the same across the board, no change. Okay. So I don't care about B, it's not helping me. What is helping me is that A here is doubled, right? So 5 over 2.5. That's essentially equal to 2. So we know it's A to something power. So A to that something power. And we know that this side is 3.5 over 1.75. If you notice, I'm not writing the 10 to negative 3 because these are the same thing. I'm just saving myself some time. These are the same values. Okay. This is also going to be equal to 2. So this is telling me that 2, the rate has doubled, right? When I double the concentration. So how does doubling the concentration affect the overall rate? And then we need to look at it in terms of the power. And this happens to be a 1. Okay, so if I double something, it's a first order. If I double something, it will also double the rate. If I triple something, it will triple the rate. Quadruple it, quadruple it. Okay. Any questions so far? Now, the next thing you want to go ahead and look at is we can look at experiments 1 and 3. If you notice, these two are the same, so I can go ahead and cross that out. This is doubled. This is also doubled. So that tells me that my B here, again, is 2 is equal to 2 to something power, and that is to the first power. And it will stay consistent no matter which combination you do, as long as you can isolate one and not the other. So if I go ahead and clear the screen real quick, if I look at experiments 2 and 4, this is 5 and 5, I can cross those out. This relationship between B and initial rate. This is essentially doubled. This is essentially doubled. So this is 2 to the 1 power is equal to 2. Any questions? Okay. So everything we just spoke about, I don't need to sit on this slide. We already know it. So it's just finding out m is equal to 1 and this one n is equal to 1. So they both happen to be first order. Together, they are overall order of 2. Okay. With that said, you can also determine the value or the overall order based on just a rate constant. Just because we've done the cancellation of the rate constant. So you know that if it comes up to seconds minus 1, it is essentially first order overall. So integrated rate laws, pretty straightforward. The only other thing you're doing is including time here. So my recommendation in terms of writing equations is always to use the straight line format. If you prefer not to, you can use any of these here. Gives you the same information. So once again, straight line format is the one right here. You'll see that it's split into something AT equals KT plus, and then here you have A0, okay? There's always some combination that we're changing what values are here and here and here, but then generally speaking, it's about the same format. So this one is for a first order. See how it's ln. So we're dealing ln of versus time, right? If I go ahead and click the next one, this is 1 over the value, and you still have everything else the same. I'm only changing what is in front of these 3 values here. So this happens to become positive in this case because it is negative and it is 1 over. So then you're just undoing the negative. Okay, and then the last one, same thing. It's always a change of what is in this box right here, these 3 boxes. Everything else is the same. Any questions? Okay. With that said, the next thing we're going to go ahead and take a look at is half-life. So you can tell by this equation right here, this is half of each of the original amount each time. So half of this and then half of this, half of that. That is how half-life works. The equation we have that we're going to focus on is simply just going to be T1/2 is equal to ln 2 over K. I don't care so much about these. I can tell you one thing. 99% of the time that people have taken the of the ACS final exam, they have not needed to use the second order or the 0 order. They have only needed to use the first order. And the reason why we use first order is because it is independent of how much you started with. So if you look here, this still tells you the initial amount of the concentration. Same thing here. That should be a lowercase 0, okay? But here, there is no A0. Any questions? Okay. So radioactivity, remember that there are 3 main types of radioactive emissions. The beta particles splits into multiple categories. Pretty straightforward. You should be able to just plug this into an equation. So they give you like the K is going to be alpha. You go ahead and draw out the alpha particle, write down what elements are coming out, how it looks in terms of mass and atomic number, and you're good to go. Okay. Moving on to chapter 17. Again, remember, chapter 17 was your make or break. Everything from chapter 17 onwards is mentioned here. So all of them talk about equilibrium. Remember your equation, product of a reactant, your coefficients here become your exponents. So make sure you do that correctly. And always make sure you balance your equation before you go ahead and try to solve it. Relation between Q and K. Q, when it's less than K, it will shift to the right. In other words, it will drive the forward reaction moving forward. Okay. If it is greater than K, it will shift the reaction to the left. And then we also can see that when we're writing values of K and Q here, the solids and the liquids do not get included in our equations. Okay. Any questions? All right. Once again, relationship, shift to the right, shift to the left. When it is equal to K, it is essentially equilibrium. So when we solve for these problems, things that you want to do, you want to make your ICE table. Okay. So fun thing about ICE table, if you take a look at all the values of the I, the initial value, this is essentially your Q. All the values at equilibrium, this is essentially your K. Change is how you are getting from Q to K. Are you moving the forward reaction? Are you moving the reverse reaction? Depends on the relation between Q and K. Any questions? All right. So we also have our simplifying assumption, also known as the 5% rule. If the initial concentration over the K value is greater than 400, we assume that the change, the minus X or plus X you find inside of a lot of your equations are so obsolete, so in other words, so insignificant that we can finally ignore it. The only time you do not ignore it is if I wanted you to find the exact temperature, or sorry, not the exact concentration after you have solved for the X. All right. Any questions before we jump to chapter 18? All right. Chapter 18, we have 3 models of acid base. Arrhenius is based on water, so H plus producer, OH minus producer. Bronsted-Lowry is essentially proton, so proton donor, proton acceptor. Lewis acid base. So remember, none of these are wrong. They just expanded on the other one to include more definition. Lewis acid base is based on electron pairs, so lone pairs of electrons. Okay, acid dissociation Ka. Higher the Ka, greater the amount of acid will separate, stronger the acid. So a strong acid means it will dissociate very easily. Weak acid means it will not. Remember, the ionization of water, this is essentially equal to your H plus times OH minus, which is equal to 10 to the negative 14 at 25 degrees Celsius. Very importantly, this only happens at 25 degrees Celsius. If you change the temperature, you change the ratio of what that number could be. It could be greater than 1.0 times 10 to the negative 14. It could be less than any combination of that if you change the temperature. And also on the assumption that if both concentrations of acid and base are equal to each other, then essentially I just have water, a pH of 7. Okay, a little bit of conjugate acid base pairs. Remember that a conjugate base is something that has lost the acid. So if I wrote HCl and I get rid of the H, this is my conjugate base. Or this one right here. Essentially F minus left. That's your conjugate base. Any questions? Someone have their hand raised?
Yes, Professor.
ahead.
So it's regarding the acid base, the Bronsted, Arrhenius, and Lewis acid. There was a question like all arrhenius. So there's there was a question on Alex, like all the acids or all the elements would be if they are Lewis, they would be Arrhenius and they would be Bronsted. There's something like that. Do you understand? I mean,
I get what you're saying. So it's kind of
Yeah.
like if it's one, can it be the other kind of stuff?
yeah, exactly.
So let me
yes.
draw you a little scale here, okay? This is Arrhenius' definition of an acid, okay? I'm gonna use a couple of colors here. And this is Arrhenius' definition of a base. So this is the two things that he's determined, okay?
Mhm.
So I'm just gonna split that up. That's a box right there, okay? With that said, Bronsted-Lowry said, hold on, you're talking about just H plus producers. So that's not enough, right? There are some things where there's OH minus. So he says that these OH minuses, these additional things, right? I'm just gonna write Bronsted-Lowry BL, okay? He said that these things also function as bases because they receive the proton, right? So they're receiving the proton from the H plus, so that means they are functioning as a base, okay? Then on the other side, Lewis expanded on this definition. He says that, hold on, acids cannot just be the ones donating protons because you need to receive electrons in the process. So Lewis pretty much said, I'm expanding on the definition of acids.
Okay.
Does that make sense?
Yes.
So if
Okay.
something is a Lewis acid, it doesn't have to be an Arrhenius acid. But if something is an Arrhenius acid or Arrhenius base, it is guaranteed to be Bronsted-Lowry or Lewis.
Okay. Got it.
Okay.
Okay. Thank you, Professor.
All right. I will consider that request and we can talk more about that later on. Okay. Okay, so once again, conjugate acid base pair is pretty straightforward, movement of one proton in the process. I don't need to spend too long on this. We pretty much covered this. If you have any questions on it, you can ask me. All right, talking about Ka and Kb. If they are a conjugate acid base pair, Ka times Kb will equal Kw in this case. Once again, this only applies if it's a conjugate acid base pair. So if I have HF and F minus, this Kb and this Ka, the two of these times together should equal Kw. Okay. If this was HCl and then F minus. These would have no relationship whatsoever. I cannot calculate that. Okay. All right. So the relationship between any of these four values, pH, POH, OH minus, and H3O plus, are directly related. As H3O plus increases, OH minus decreases proportionately. Okay. Same thing with pH and POH. If one gets closer to 14, one loses the value less up to essentially 0. So the two of them added together must equal 14. Or for the two of those, H3O plus and OH minus, two of those multiplied together must equal 10 to the negative 14. Okay. Anyone have any questions so far? Okay. Solving weak acid equilibrium problems. This is pretty straightforward. You can go through all these steps, or you can simply write it as Ka times the initial concentration of that acid. Assuming we have a weak acid equilibrium and we assume that the change is negligible. This is essentially equal to your X, which is equal to your H3O plus concentration. So your H plus is equal to your square root of Ka times your initial concentration, whatever that initial concentration is. Okay. Any questions? All right. Now, really quickly, do I need to use an equilibrium equation, in other words, an ice table for a strong acid? Yes or no?
No.
No, right? Because all of it dissociates. So if I had 0.3 molarity of HNO3, right, I should have 0.3 molarity of H plus. Okay, and with that H plus, I can go ahead and switch this into pH. I don't need to do any kind of additional changes with it. All right, any questions? Okay. There's one other thing I do want to bring up here. This is just so you don't make the mistake when it happens. I have here calcium hydroxide, it's CaOH2, okay? How many hydroxides do I have if I had 3 molar or 3 molarity of this thing, or 3 moles? How much OH minus do I have?
Is it 6 per?
It is 6 right here, okay? And the reason why is because this is doubling this. So there's 2 OHs for every 1 mole of this substance, okay? And so if there's 3 of them, there are a total of 6 of them. Okay, any questions about that? This goes back to stoichiometry. All right. With that said, well, we don't need to spend too long on this. Again, we assume that the assumption rule always applies, the 5% rule, because it's barely dissociating. All right. So let's talk about this one. We're going to talk about the salts. This is where a lot of students get confused. Before we talk about the salts, I'm going to draw you a scale. Okay. This is the strength of your conjugate bases. This is the strength of your acid. Okay. If I have a weak acid versus a strong acid, which one is stronger? Not a trick question. Which one is stronger, the weak acid or the strong acid? The strong acid, right? So acid strength is increasing as I go up to the top here. But also as a response, the conjugate base, it increases in the opposite direction. Okay. So example I can give you here, I'm going to go ahead and just pick an example here. I have HCl, and then here I have HF. Okay. With that said, their conjugates are essentially F minus, and then on this side, it is Cl minus. And the way we can go ahead and compare this is to say that F minus is a stronger conjugate base compared to this, a lot more stronger, because HCl is a lot more stronger compared to HF. That make sense? Now, there's also relative values we can put in here. That relative value happens to be H2O. So chlorine negative is weaker than water. Water is a better base than chlorine negative. The next thing you know, F minus here is a greater base than H2O. So it's going to go ahead and jump in there and replace something. Any questions? Okay. When it goes in and jumps in there and takes away an H, it will go ahead and leave OH minus left over. That is why the solution becomes basic. For a neutral solution, it's usually strong acid, the cation of a strong acid, the anion of a strong base. And the two of those joined together, they both don't react with water because they both like to remain separated. They are weaker than water, both scenarios. All right, anyone have any questions up to this part right now? Okay. Again, for acidic solutions, you have the cation of a weak base. This is the one that wants to return to being NH3. So it does not want the NH4. It is going to get rid of that one H. That one H is going to only go on water. So then this becomes H3O plus, and that is why you have a little bit of an acidic solution. Any questions?
Could you explain that again, please?
Sure. So right now, what I have here in this solution, right, is NH4 plus. Okay. I also have Cl minus. Cl minus is a weaker base compared to water. So this is not going to do anything. It's so weak that water is stronger than it. Okay. So I can put Cl minus to the side. I don't care about it. It's there. NH4 plus. This is the conjugate acid to a weak base. So that means its acid strength is stronger than water. Not stronger than the regular acid, but it is stronger than water. Does that make sense so far?
No. Could you explain the conjugate acid and weak base?
Okay. So just as we did before with the acids, right? The stronger the acid, the weaker its conjugate base. Okay. The conjugate acids and bases work the same way. The stronger the base, the weaker its conjugate acid. If I look at NH3, is this a weak base or a strong base?
It's a weak base, right?
It is a weak base. Okay. So the conjugate acid, right, is going to be a stronger acid than water. The comparison is always to water.
So a stronger acid, but not a stronger base. I mean, not a stronger acid than water, but not strong.
Not
acid.
strong, but stronger than water. Water is pretty weak. Okay.
Okay.
So it's not like I'm not saying this is a bodybuilder. This is just bigger than your next door neighbor or stronger than your next door neighbor kind of stuff. Okay.
Got it.
All right. With that said, the only source, so another way to look at this is NH4 plus does not want to stay as NH4 plus. They always want to return back to their weak base or weak acid originality. So this is going to want to get rid of that one H. It doesn't want that. It's going to throw it away. The only person who's going to receive it is going to be H2O. And once again, that will form H3O plus. So the solution is slightly acidic. It's not like I'm changing this entire solution to a pH of 1, like pepsin in your stomach. I'm only changing it very slightly. Okay. Another example would be highly charged metal cations. These are the ones who also go ahead and cause the reaction to become acidic. Then you have basic solutions. This one is the opposite. This is the conjugate base of a weak acid. This is stronger than water. It will be the one that takes away the hydrogen from the water, forming OH minus in the process. Okay, any questions so far up to this part? All right. For solutions of weak acids and weak bases, or the cations and anions of each one, then you need to go ahead and look at the Kb and Ka values and then convert and find out which one's a stronger one, which one's a weaker one. Okay. Everything still applies as long as you understand the relation between conjugates and its original value. So conjugate base and its acids, and then conjugate acids and its bases. You should be able to figure this stuff out. Any questions? All right. So let's move on to chapter 19 here. This is your same thing. We're still dealing with equilibrium here, but this time we're dealing with titration. So we're dealing with buffers and titrations. Okay. So this is done with a common ion effect. Yes. Conjugate acid of a strong base is so weak, it's weaker than water. I don't even consider it, I guess even at that point, if it's even considered an acid, it's weaker than water. Okay. So this one, the relationship about this is the common ion effect. So this is a weak acid plus its conjugate base. You have some amount of both. And this is essentially forming a buffer. It prevents the pH of changing, which prevents H plus falling into the solution itself. Okay. So if I suddenly add H plus, I suddenly add an acid, the conjugate base is going to react with it, and the two of these are going to go ahead and form my weak acid. So I'm making more of what I already have and using up something that I had here. And that's what's happening with this H plus. It's not sitting in solution of water. Okay, it's actually being used up in the process. The opposite is true if I add in OH minus. So this thing right here needs another H plus. It's going to pull on H. The only source that's going to give up is the weak acid. This is going to leave, join together. The two of these are going to form water. And what I have left over is just this. So I'm making more of this, and then I'm using some of this. That is how our buffers work. Okay, any questions? All right. With that said, the Henderson-Hasselbalch equation is the only equation you use, or the only time you use this equation is for a buffer. And this base is referring to conjugate base. This acid is referring to usually a weak acid. And then the opposite scenario is if I wrote the Henderson-Hasselbalch equation with POH. This is POH PKB plus log of your acid over the log of your base. Okay, any questions? And with respect to that, conjugate acid and weak base. All right. So preparing a buffer, pretty easy. You want to find a weak acid with the pKa that is close to the pH you want. Then you adjust the ratios of your conjugate base and your weak acid to get that number that you need. Best way to make a good buffer is high concentration, and the two concentrations are equal to each other. Remember, a buffer is good at preventing both acids and bases. You could make a buffer that's good at preventing just bases and not acids. It tends to lean to one side or the other. Okay. But the purpose of a good buffer is to resist the change for both sides, either acids or bases. All right. So moving on to this part right here, this is where we talk about titration. Some of you may have gotten confused in this area. The best way to look at this is always to look at your beaker. What is inside of my beaker? I should have some acid in here if I started with it. How much base did I add in? What happens when the two of these are combined? What do I now have in my beaker? What is here? What is this formed? What is left over? Things like that. That is all you really have to try to figure this out. In the very first one, I have not added in. We're looking at strong acid, strong base. So an example I can give you is HCl and NaOH. Okay. Here, none of this exists. There's nothing in there. So this is just going to be whatever that pH value here. Okay. In the bottom scenario, I have a lot of my acid. I'm not adding acid. It's the same amount, but I've added in a little bit of base. So by the time I'm done, all of this base is used up. The remaining is going to be just your acid. I don't care about what it forms. It probably forms water. Again, the water is not going to be significant here. You can get the concentration by putting this together. Moles over the volume gets you the H2O plus, and then you can get your pH. All right. Any questions? Okay. pH at equivalence point for strong acid, strong base, fully dissociated, so that's pH is equal to 7. They cancel each other out. And afterwards, I have a lot more OH minus. This is going to be the one in excess. I'm going to use up all of my H plus. I don't see it written here. There we go. So all of my H plus is used up. I just have some OH minus. I go ahead and do the calculation. I can solve for my value of pH. Okay. The more important one is your weak acid, strong base titration. This is the one that they tend to focus on. Okay. In that first step, this is just your weak acid equilibria. You can go ahead and plug that in. This is some concentration of weak acids. How much H plus comes out of this? Simple as that. The next one, this is where it gets a little complicated. Okay. So I want you to follow with me what I have here. I have an acid and I have a base. Okay. And I will simply say that I'm making up a number here, 10 and 7. This is the amount of each one that I have. When I join these together, all 10 is going to react with all 7 here, and I'm going to have left over. So by the time I'm done with this, this is now 0, this is now 3. Does that make sense? So I'll rewrite this. My base is 0, my acid is 3. But I have formed something here. When my acid joins with this base, okay, the H is disappearing. I'm taking that away. What's left over is my conjugate base. So I have some conjugate base. The amount that I have is all the amount that has of my acid that has reacted. So I should have 7 of my conjugate base. So this is what you have in your solution. This is your before and this is your after. You've added this much in. This is what it looks like when you're done mixing it. Any questions? With that said, I have some kind of weak acid, some kind of conjugate base. It's great to plug into this equation right here. All right, and that'll give you information such as a pH value. Okay. So let's continue. At equivalence point. So same concept here. This is the same as if I said 10 of my base, 10 of my acid, the two of these combined, I should have 0 of my original acid, 0 of my base left. But remember, because this is a weak acid, if I take away the H, right, this is going to suddenly become the conjugate base. And the amount of conjugate base is what you had here. So 10 conjugate base. Now we know that this is we can still say that this is a weak base, but it is still a base. So what we can say is that the pH at this point right here, okay, this should be a value greater than 7. Because we know that this is slightly more basic. Not a lot more basic, but slightly more basic. Okay, anyone have any questions? All right. Now on to the very last one. pH beyond equivalence point, you are just simply looking at how much OH minus. In other words, you're looking at how much, drawing this here. You look at how much of my base is left over, my excess base. So by the time I am done with this A is all gone. I have maybe 5 of this base left. My conjugate base is there. I have 10 of these, but this is so insignificant compared to this base. This one is going to be so much bigger, right? That I can just ignore that. This is just how much I have because this is a strong base. Any questions? All right. So formation of a precipitate, only thing you need to know is that when QSP is greater than KSP, it will form precipitate by moving in the reverse reaction. Because remember, the equation is solid changes into an aqueous and aqueous solution. Okay. If Q is less than K, it will not move to the right. If Q is greater than K, this will shift to the left. Okay. Sorry, when Q is less than K, it will shift to the right. When Q is greater than K, it will shift to the left. So we are looking at taking these two aqueous solutions, two things that are dissolved in water. I'm trying to put them together and I'm forcing the reaction to go to the left. In other words, I am making the solid. That is why there is a precipitate. That is essentially the solid. Any questions? All right. With that said, jumping on to chapter 20 real quick. Entropy is a measure of disorder. We have different ways of increasing entropy. Increase the temperature, give it more freedom of particle motion for the diagram. Usually formation of a solution will give you that. The larger, the more complex the size also contributes to that as well. Okay. Freedom of particle motion, this is the main thing. This is what makes something spontaneous. You have the freedom to move around. That is what essentially makes this spontaneous. Okay. All right. With that said, the first law of thermodynamics was just energy cannot be created or destroyed. Second law is where we determine if this is going to be spontaneous or not. As long as the delta S of the universe is increasing, then the reaction was spontaneous. So you could have a system, in other words, an experiment that decreased the entropy overall, but your overall surrounding of what you've generated in the process is positive, so it makes the entire thing positive. Any questions? All right.
Can you repeat that, Professor?
Sure.
Last question.
You want delta S of the universe to be positive. If this was negative, as long as the delta S of the surrounding was positive, but a greater value compared to this, then the overall will come out to be positive.
Okay, thank you.
I can try that for the next time. If you want to work in groups, I can randomly assign groups in breakout rooms, things like that. If you want to work in groups on those things, I'm fine with that. If that's something you guys want, you can send me an email and I'll try to put that together. Okay. Right now, we're just doing concepts. So once we get through the concepts, next week we'll do all of the questions.
Professor, can I ask one question regarding
Sure.
the last topic? So would it just mean that for a process to be spontaneous, the entropy of the system must be higher?
No.
than
So
the surrounding?
entropy of the system doesn't really matter. I
Okay,
care if we want it to be spontaneous, the entropy of the universe must be positive.
Okay,
Okay.
got it.
What happens
Okay.
in the entropy of the system, which is kind of like usually a lot of times your experiment, it could be negative. Okay. You could actually be very ordered in the process.
Mhm. Okay.
So an example I can give you. Okay. Actually, I can't think of an example off the top of my head, but you organize something, but you go ahead and throw a bunch of things outside. Okay. So that is actually making things more positive in this sense with disorder. So the overall is still positive because this is greater.
Okay.
Okay.
Okay. Got it. Thank you.
All right. Now, next one is relation between delta S surrounding and heat. Remember that it is the opposite sign. So if something is exothermic, then your delta S surrounding is positive because it is receiving that heat. Okay. If I'm releasing the heat, that heat has to go somewhere. So the surrounding is receiving that heat. It is becoming a greater entropy. In other words, more disorder. And then we have the equation Gibbs free energy. This is usually done if you see the word system. So that's usually they write it as standard state or they just write it as system. Okay. Either one is usually the case that you'll see. So in other words, these are all in standard states sometimes. So we're in this scenario here. You want to make sure that the delta G is negative. That is your goal for spontaneous. Okay. In other words, spontaneous in chapter 20 again means forward reaction, moves it to the right. So it's not necessarily a problem if it moves it to the back, or in other words, to the reverse, just that this is not spontaneous and it does not happen on its own. All right, any questions? Okay, I'm going to assume you already know the general chart, the relation between your delta H, delta S, and then your delta G. And your goal is to get it to be negative. If they're the best way to remember this is if this is negative, this is positive, you already know that this is always spontaneous. If this is positive, this is negative, you know this is never spontaneous, right? And then down here, these two are both positive values, so it's a higher temperature. These two are lower values, so it's a lower temperature. Hopefully that's one way to remember this. The lower the temperature, the more spontaneous if they are both negatives. Okay. So other equation we need to know is your delta G at standard state, which is essentially equal to your delta G minus, which is equal to negative RT ln K, which we can expand into the original delta G and include that into the equation. But also tells us that Q is equal to 1 in this case. And 1 could be 1 ATM, 1 molar, whatever else they use as a 1 value. Okay, with that said, you can expand it into the delta G of all scenarios here. This is at standard state right here. This is your R, this is your T. Remember this R right here. Once again, if you don't see anything with pressure, this is your 8.314. All right, any questions? All right. With that said, we won't spend too long on chapter 21 just because you did just learn this. So I'll go through this as quick as I can. You know, it's NOx, Leo says GER, loss of electrons, gain of electrons, reduction, things of that nature. Hey, half reaction method, remember that you balance your acidic, you do your acidic steps first, and then you do your basic steps. Doesn't require assigning oxidation numbers, pretty straightforward. Standard reduction potential or standard electrode potential, never change the signs of these things. Put in the number that goes here, put in the number that goes there, subtract the two, and you get your answer. This should be a positive value. Anyone have any questions? Okay. The hydrogen electrode is just your reference point, so everything is based off back into hydrogen. So if you ever see hydrogen in something, you know hydrogen is going to be equal to 0. Okay, a little bit of a relation between free energy and work. So we're combining delta G and E cell. So we can combine it with the equation negative NF E cell, and we end up with our two equations here. These equations look very familiar to you. This is under the assumption at 25 degrees Celsius. That's what 298 Kelvin is. So I can essentially say, I don't want to deal with this constant. This is now a constant. It's 25 degrees Celsius. This is a constant, and part of this is a constant. So when you convert everything into the log, plug it in, and you should be able to solve for what you need, or simplify it here. Okay. Any questions? All right. So relation between delta G, E cell, and K, you already know this slide. I don't need to spend too long on this one. And moving on to the Nernst equation, this is where we go ahead and take that full equation that we had for just like our delta G and delta G as standard state, apply it in this case for our E cells. Same situation, rewrite it with 25 degrees Celsius. So this, the Nernst equation 0.0592 becomes log of Q. And if we're dealing with concentration cells, this would be 0. And in this case, we're not, so this is not 0. All right, any questions so far up to this part? All right. So, oh, there's a link for the evaluation, okay? I'm gonna go ahead and just copy that for you right here. Oh, you can just go ahead and type it in as well. Usually that's the link that they use. Pretty straightforward. I don't know if they want to include another line like that. Sometimes it requires that. This is be as honest as you can be in terms of the evaluation. The only person who sees the comments is me, and it'll be after the semester is over. Usually by the time the next semester starts is when I get to see those comments. Okay, so no one else sees the comments. The only thing that other people see are the ratings in terms of the numbers. Okay, with that said, that's all I have for today. We will go ahead and do practice questions next week. And then I will also go over chapters 18 and 19 next week. There were some technical difficulties this week, so I didn't get to all of it this week. Yes, go ahead.
Yeah, hi, Professor. I was just gonna ask real quick. I forgot if you answered this, but did you grade the last 2 quizzes?
So I just said that there were some technical difficulties last time, so chapter 19 was a little delayed. So I didn't get to grade all of chapter 19. Some of you already have it graded, some of you have not. So I'm also gonna do another double check, triple check afterwards.
Okay, sorry.
Okay. All right. Any other questions? So there will be office hours today. It'll be a little delayed, so I need about like 10, 15 minutes. And then if you have any questions, you can ask me there. Okay.
Have a happy Thanksgiving, Professor. Thank
You
you
too.
so much.
No problem.
Have a good day.
You too.
Bye-bye.
Okay.
Thank you, Professor.
All right. Okay. So no other questions. I'm going to go ahead and close everything. I'll open it up in about 10, 15 minutes for office hours.